Thanks, everybody. I think some people here know me, but it's always great to meet new people, and there will be a shameless plug for our ClueCon Weekly program somewhere down the presentation, of course. Who am I? I'm Luca. I'm lead solutions architect at SignalWire. I've been here since day 3 or 4, and we've done a lot of interesting stuff with the company over the years. And I work with large and small customers, helping them use our APIs. I've been in RTC for a very long time, actually starting with FreeSwitch around 2008-ish. I was playing around with FreeSwitch, transition from web development to RTC, and properly using FreeSwitch for about 10-ish years. I'm a Ruby developer, but I know a little bit of everything. Had to learn more over the course of the last year or so, where we started really working with AI. I also host ClueCon Weekly. It's a great podcast about the open source industry and the RTC industry. Anybody wants to come on and join, come talk to me after the presentation. So my goal is to explore first what AI is today to set the stage for what we're going to look at and the research we did and what we developed out of that research. AI started in 1950 with Alan Turing and all of the other very well-known developers and pioneers of the period. And at first, it started around heuristics. So it was an idea of programming software to behave like it will be like an expert would. So you will actually code the rules yourself, saying, OK, so if you're playing chess, if the opponent is making this move, then you make this move. That will be an expert system. The idea of the more knowledge, the more code you put in, the better it will be. And that didn't work really well. And in 1970s and in 1970s, we got the first what's called the first AI winter. So effectively, the industry sort of stopped working in AI because expert systems were good for a variety of usage, but really within, my opinion, and well, people are better than me's opinion, is that there was not enough computing power at the time. So you could only do very limited things. So AI looked like it was a novelty, so it ended up being abandoned for years. In the 1980s, with the advent of more computing power, linear algebra bled into IT technology. We got neural networks, backpropagation, and the idea that you could train a machine to learn instead of having to tell it everything it needs to know. And that's where we've been starting our journey took us towards LLM with the success of machine learning used in finance. A lot of the big funds that made billions over the years started between the 80s and the 90s. Think Renaissance, Jim Simons, there's a lot of that. Of course, during the 90s, we started seeing real good stuff, like Deep Blue beats the world chess champion, Kasparov, and in 97. Right now, it's impossible for a chess player to beat a fully powered AI. It's the way past. Like even Magnus Carlsen, whoever, cannot beat a full power chess AI right now. It's simply impossible for them. Then we go into data science, the emergence of data science. In the 2000s, we had more memory. So first we had more computing power. Now we have more memory and more disk space. So we can start working with huge data sets that allow us to analyze and derive behaviors from large sets of information. Of course, that's when we also start having computer vision, autonomous systems, robotics, and all the other interesting stuff. Of course, then we have last remaining pieces, natural language processing. So using the power given to us by neural networks and the power given to us by large data sets, we go into having a machine learn how to process language. So know what a word means, know what a word's context means, and what the significance is. And then we get to the first, Deep Blue and Watson, IBM's Watson, finally manages to win around the Jeopardy, which is a popular US quiz show, showing that it can interact in real life. That was, aside from it's the funny thing of winning a quiz show, it's still an important milestone because it proved how the entire system was working. Of course, we also got a minor milestone in 2016, which I always like to point out. Go is kind of, I don't want to say Japanese chess, and I'm sorry for saying that for all the people who are here who like Go and play Go. It's a very complex grid-based game with white and black stones where you sort of try and capture areas of the board, to say it in one sentence. But it's considered the world's most complex board game. And for a long time, a computer could not even play Go properly. In 2016, we got to the point where AI could beat the world champion. So Go was beaten almost 20 years after chess, to give you the comparison of how complicated it is. And we got there. And then right now we have LLMs, and we have a lot of growth, we have a lot of interest, and ethical and regulatory discussions. Is it good? Or what are we doing? Is it going to work out? And there's a lot there that needs to be addressed. But for now, let's see. So today we have LLMs and ML and RNN and all sort of alphabets we're really fond of as engineers, right? It's all we do all day, find new acronyms. It's really, our industry really produces acronyms more than anything else. We have two main approaches. Supervised versus unsupervised learning. Supervised means you give the machine instructions. Unsupervised means you give the machine data and it derives the instructions. Now we're using LLMs, which are neural networks trained on very large language data sets. Very, very simply, what an LLM does is nothing else than trying to decide what will be the most statistically probable word following a sentence. That's all it does. So when you're trying to when you're using an LLM, all it is doing is comparing the context you've given it and trying to write sentences using the most probable word by word, or sentence by sentence. And that means that an LLM is very good at writing and generating context, but for example, it's very bad at calculations. But more importantly, and this is where we're leading, is not necessarily correct. What does not being necessarily correct means? Remember, an LLM just derives the next word from what's been, let's say, from what's been ever put on the internet or written. So it just knows that. An example I like to make is, and we'll use that throughout the talk, is I want the LLM to tell me what the most popular ice cream flavor is. The LLM doesn't know what the most popular ice cream flavor is. It will just give you the word that more often follows that sentence or similar sentences in what's out there in the internet. So it can be skewed by the fact, for example, that maybe it's never found someone who likes strawberry because that's never posted on a blog post. So it doesn't know. But that answer is not correct. That's not a market research. It's not reading a market research and finding out that the most popular flavor is chocolate. It's just literally that most people like chocolate according to all its read. An answer that is wrong at the level of correctness but looks correct is called an hallucination. Another example I like to make is I've been helping a friend work out a solution that's based on legal analysis of laws and to give legal information about cases and stuff. And sometimes before we found a way to really ground that platform into truth, it will literally make up law numbers or judge sentences. It will say, so according to sentence 1 to 3 from 2020, this thing is illegal. But then there was no such sentence. And even the name of the judge was made up at time. Like there was no such judge in that tribunal, and there was no actual sentence. And the LLM, again, doesn't really know which is the most popular ice cream flavor. It will just complete the sentence. So how do we help that? There are a few ways you can make an LLM perform better. We'll focus on one today. Prompt engineering is a way to optimize input and output by asking the LLM the right question and asking it to output the result in a certain way so you can make it better and use its power to better effect. Fine-tuning is generally used to specialize the output on specific scenarios, meaning that you can give an LLM an extra round of training to make it more of an expert on a narrow set. So you could technically do fine-tuning about the ice cream, and then you'd have a perfect LLM that's an expert on all things ice cream, but it will only know about ice cream. If you were then wanting to ask it questions about the favorite flavor of donut, that's been that's most liked out there. You will have to do another fine-tuning with another LLM that will only be the world's foremost donut expert. And that goes on and on. So fine-tuning is only for certain use cases. Agents are more of a technique than a natural, way of interacting. Agents will be you ask the question more than one time in very briefly. So dividing a task into components. So first thing you do is ask the LLM, okay, how will you solve this problem? And the LLM will say, I will find the data here, and then I will check what the data says, and then I will answer. That's for making the LLM perform better. RAG is the way you get truth grounding for LLMs. You make it more knowledgeable by simply helping the LLM respond with the right information. So RAG is retrieval augmented generation. It's a common term that's come up recently. You can find it all over the internet. I don't know why they chose such a complicated acronym. Frankly, you could have done a million other ways. But and by the way, the pictures you see in the presentation, I just gave the presentations to ChatGPT and asked it to generate some pictures for the presentation. So they're cool. I just wanted to see how it looked like in this was RAG, retrieval augmented generation. I gave it the document and asked it to answer questions. So what RAG is adding information to the prompt to ground the response with facts. It's used to make the AI knowledgeable about a domain, but without tying the AI to that domain only. It means you can ask a question about cake, or a question about ice cream, or a question about donuts, changing subject, and it will always respond correctly. Helps get around attention context limitation. So every LLM has a context size, meaning that you can only write a question that's a certain length. Contexts are getting bigger right now, but you couldn't give, for example, an LLM 3,000 pages of text to describe the problem and then go into ask it questions, because it would not fit in the space it has available. Plus, very often we'll see one problem that sometimes come up, which is redundancy. You will ensure the right information is used. The description of RAG is simply, I will store the content into some kind of database and retrieve the relevant documents at prompting time, meaning that I will look at, so the user wants to know about ice cream, so I will retrieve the relevant chunks of text from the database that talk about ice cream and just give those to the LLM. That's actually to get to production. There's quite a bit of work you need to do to get RAG to work properly. And I've broken it down the way it's usually done, but it's also how it works for us. You want to ingest documents, so you have a lot of documents. You have PDFs, Word documents, maybe scans, images, whatever. You want to take the documents and grind them down to the text you need to store. Then you divide that text into components that are useful for the LLM. Maybe process them a little, maybe normalize, make them all the same length, ensure you can find them, store them into some kind of database, and then find them at runtime. So let's go, and then after all, use the prompt to find those documents. Let's go through the journey of getting to the ice cream response, starting from ingestion. Of course, ingestion becomes more important as document complexity increases. So if you have PDFs that are just blocks of text, is not a problem. If you have PDFs that have tables and images and all sorts of, and plus PDFs are very common in the industry, but are also not very standard inside. As anybody who has tried to extract text from a PDF, there's all sorts of things in there. Some PDFs are actually just scans or images, like it's just literally just a slideshow. So figuring those out requires a few choices. It's very, very important, probably one of the most important steps, because the rest you can get around, but if you're not reading the documents properly, it will never work. There are two main strategies, extracting the text or doing OCR, so character generation, plus or minus using other LLMs to read the data. The main question is, do you need the structure? Do you need tables and images? Or is it just a long list of text? Then you can get away with something simpler.
Okay.
A few options we have in the app we used, and a few options there are in the market are from the super simple PDF to text. It's just a command line tool that will just take the text that's in a PDF and output it as plain text. It's great for very simple extraction. Pymo PDF and a bunch of those are, there's a Python space is the de facto data science language. So there's a lot in Python that's used to treat data, extract data from documents. PyMO-PDF is great. It's very structure-aware. It can do a little bit of tables. It can do a little bit of headings and paragraphs, not images. Tesseract is an OCR engine, so you will just convert the PDF to images and then try to read it. It's very good, but of course it's heavy. Like, of course, doing visual recognition on documents will take a while. There's a couple established document converters, Apache, TCAP, Pandoc. They're all pretty good. You get text out of a lot of different document types. They're pretty good. They're not fantastic, but the good thing is that they do have a lot of, they support a lot of formats. In the cloud, if you're not afraid of privacy concerns, there's a couple very good solutions. Azure Document Intelligence and Llama Parse are both great. They will give you a lot of structure, a lot of quality. They're not free, of course. Document Intelligence is actually quite expensive, but it's also great. It will turn any format into usable information. It's really, really good. My personal preference is, if you're running something locally, run PyMO-PDF, the 4LLM version, which is very good at a lot of things. Or use Azure Document Intelligence. That's honestly great. Or you can use Tesseract to do the OCR. Once you've read through the document, which in our case will be the market research PDF about the favorite flavors of ice cream sold in the US and last year, you want to divide those chunks into components you will fit into the prompt. So as we said earlier, you can't feed the entire document into the LLM because it won't fit. It's too much. You just will not be able to respond. So you want to divide it into significant chunks. Why? There's two reasons. One, context is too long. Second, well, three reasons. Second reason is the attention window. If you give the LLM too much text, it will not pay attention to the text in the middle. That's a proven phenomenon. Not all engines have it to the same level, but you don't want text to be too long because then it will only really get information from the start and the end. And redundancy. This is what I was saying earlier. Sometimes you have information that's very close to each other and only differs by a word or a number. So maybe if you're looking at different contracts, the only difference between contracts might be the number on them, like the cost of the contract. So you don't want to give all the contracts to the LLM because it will get confused. You want only the contract you want. And here's an example of chunking strategy. Oh, that blue isn't great, but this is my little document example that contains there's information about how much ice cream is sold every year, then which one is the most popular flavor, and then which state eats the most ice cream. These are made up. I don't know if you're from Texas or Wisconsin. Wisconsin certainly likes their ice cream, but I don't know if California is the most consumer of ice cream in the US. Chunking, so dividing text into blocks can be done a few ways. You can use by page, sentence-based. By page will mean every page is a chunk. Sentence will be take the sentences and store them. Structure-aware is best if possible. If you can extract titles, if you can extract paragraphs, you get a much better result. After dividing the text into chunks, you might want to do a little bit of processing. You can maybe keep the name of the document you got the information from, so you can search that title too. So when I'm looking for market research, I will only search the documents that have market research in the title, and then search ice cream in the documents to make sure that I get the most relevant information. Previous and following chunks or related chunks, for example, mentions. When you're talking about laws usually mention other laws. They say, like this other law says, this is illegal. So you want to keep the relation. And you can do a lot of that with LLM pre-processing. And getting related data is very important in a lot of complex scenarios. Not in our ice cream scenario, so I think we can move on. OK, so now I have my little market research document. It's divided into little paragraphs. Each one has some information, how much ice cream is sold every year, which are the most ice cream loving states, and which is the most popular flavor. Now I need to store it somewhere so I can find it when I need it. There are two main choices, vectors and full text. Vector databases convert sentences into positions and numbers and then compare those. So they're better for for comparing entire sentences. Full text database perform classic Google-like search. You search for a word and you get the results. Both are useful to ensure correctness, and very often you will need some kind of storage to keep the original files just in case. Here's an example of how vector storage works. You convert words into an array of numbers. You compute the distance score. And it's effectively the reverse of how the LLM works. Originally, the LLM, GPT, was trained by turning a lot of text into numbers and then storing those numbers. I have put a quick example of how we do it in PG Vector just to show you that it's really just arrays. So we embed we create the embedding for which is the vector of numbers for the sentence, store the sentences in the database, then create another embedding which is for the question, and then we compare the distance between the two. Effectively, it's the distance. If anybody was familiar with linear algebra knows there's a way to compute the distance between those sets of numbers, and that's what you're going to do. It's just a distance. It requires an LLM model to do indexing, and it requires an LLM model to do the query, because as we said, we're just doing the reverse of what was done to train the LLM originally. And it's done by comparing distance. Full text search is classic search. Again, we store the words. It's able to do stemming and stop words. So if you're searching for, I don't know, ice cream, you'll also, well, ice cream is uncountable. It will do singular and plural. So if you're searching for cats, it will also find cat. It will know that it's the same word. And it is not effective with large blocks of text. So if you want to search for single words, it's better to use full text. If you want to search for entire sentences or context, it's better to use vector. Where do I store my vectors? There's a few dedicated storages, ChromaDB, Pinecone, V8, and a million others. There's been an explosion recently because, you know, it's the popular thing to do. And there's Elasticsearch, was a very good full-text storage engine. It also has vector options now. And then there's database modules. The one I personally choose was Postgres with the full-text module and PG Vector extension. I already had Postgres. It's very fast, it's easy to tune, and it's a known quantity. By no means this is the only way. I mean, the goal here is presenting with it, and we picked PG Vector and Postgres, but it's not necessarily the best way. Although, again, it's very easy to use, very powerful, and you probably already have it. So I always try to not introduce too much complexity in a stack. OK, now I want to find the chunks I put in. So there's a specific query. Which one is the most liked ice cream flavor in the US? The vector will find generally relevant chunks, but it might be misled by repetitive content. What this means is what we were saying earlier. If you have a lot of paragraphs that are very similar and only differ by a number or a word, vector will sort of get thrown off because they will all look the same. While full text, you need to first find the keywords for the sentence you're asking. So if the question is most popular ice cream flavor, you want to search for ice cream. You need something that will give you the ice cream word, and then you can search for full text, but it will find those chunks very precisely. Once we have, this is a very important step. Retrieval is, again, a very important step, because if you give the correct chunks to the LLM, it will usually respond correctly. Best way to improve retrieval quality is using both ways. So I search for the full sentence in the vector database, but I also search for the single words in the full text database. Then you can put together the results in two ways to get what are the real relevant chunks. One is co-ranking, so you can ask the LLM itself what is the best. Literally just give to GPT, hey, GPT, tell me which one of these chunks is better. That was time-consuming, token-consuming, but it works pretty well. Or you can do what's called RRN, reciprocal rank fusion, which is really just assign a score. So you have one list of results from the vector, one list of results from the full-text search, and then you just see which ones are in which position and sum the scores, sort of like a championship. The ones who have the most points are the better ones. That works, and we've been doing that a lot. Of course, once the chunks are right, you won't need much work here. What you do is simply what you see on the right-hand side. According to the following information, which comes from my pretend research, in 2023, the flavor of ice cream with the most sales was vanilla. Answer the following question, which is the popular ice cream and most popular ice cream flavor. This will not only respond in a correct, English-wise correct way, but it will also be correct in the sense that the data will be correct. It will actually say it's vanilla, not chocolate, like I got at the start. Because at the start, chocolate was just the most present word in that sentence. Of course, now you also have an interesting thing you can do in your application. That chunk I found, I know where it comes from. So maybe to the side of this, you could picture an application having a link to that market research document. So if someone wants to know where the information comes from for that response, you can give the response, and it's easy to create a very powerful and very interesting platform. And well, we're just about time. One more thing. Okay, I had to do it. Sorry, I know it's a Steve Jobs thing, but one more thing. At SignalWire, today we're launching Datasphere, which is our API for indexing and retrieval. It has endpoints to ingest and search the data. It's embedded in our agent flow, so you can make an agent know things it needs to know before it interacts with the users. It supports multiple chunking strategies, sentence, page-based, and window-based, so just blocks of text. And it's available today thanks to the effort of engineering and product that put the link up for documentation about half an hour ago. And well, go check it out. Let me know how you like it. And I hope the presentation was good. I was hoping I would have a little bit more time, but it is what it is. But come ask me any questions. Super happy to help. Super happy to explain and explore anything you might want to know. Thank you very much.
Thank you, Luca. We can have one question for Luca publicly, but he's here for the rest of the time, so you're able to talk to him direct. Does anybody want to ask a quick question of Luca while we're here? Yes, this one over here. I'm going to hand you the mic, sir. Very good.
Thank you very much. Very good talk. Just a quick, what open source large language models are you basing your stuff on top of? Are you using Llama 3? What were you building on top of?
Llama 3, there's a lot of experimentation around Mixtral right now. Mixtral, the one with the X, because the multiple agent version is
Mistral?
very...
Mistral?
Mistral.
Mostly Mistral? Okay.
Yeah, no, we're mostly Llama now. Okay. Llama 3, because it's very good. But Mistral is smaller, and we're having good results. All of this is research, so we're still, evaluating. But Llama, the quick answer is Llama.
Great. Do you feel your question was answered, sir? Good news. Okay. Well, thank you very much, Luca. One more round of applause for lovely Luca.
Thank you.